For the first time in human history, we can directly observe the very earliest stages of a planet's birth. Effectively, we are watching embryos of gas and dust slowly sticking together, some 370 light-years away. But before we understand how a planet is built, we need to know where this disk comes from in the first place. Every planetary system is made from the enriched materials of previous generations of stars. Over billions of years, old stars exploded, creating heavy elements and scattering them across interstellar space. These enriched materials, collected in giant molecular clouds, collapsed and formed new stars. The leftover material surrounding them turned into a disk. This disk is full of ingredients: silicates for microscopic rocks, iron and nickel for heavy metals, and space ices like frozen water, methane, and ammonia. But for years, we could only see these disks from afar, as a blurry blob around a star. The problem was, we knew the end result, but what exactly happened in the middle was always just a guess. Until 2018, when something unexpected happened. Planet-forming disks are filled with dust that severely blocks visible light. This dust is made of particles smaller than a micron, so tiny that they scatter light rather than letting it pass through. For years, telescopes had two problems: poor resolution that couldn't see the tiny details of the disk, and the wrong wavelength because visible light couldn't penetrate the dust. Scientists were forced to rely on computer models. One of the most famous models suggested that planets first form in the cool outer regions of the disk and then migrate inward. But there was a huge problem. No one had ever seen it. So, for years, a fundamental question remained unanswered. Is this really how it happens? When James Webb started its work, it created a revolution. This telescope can see in infrared, wavelengths that pass through the particles instead of being scattered by the dust. On the other hand, the ALMA array in Chile was working in millimeter wavelengths, which also had less scattering. Combining these two allowed us to peer inside the disks like never before. The first target, the PDS-70 system, one of the clearest examples we have today. It's a 5 million-year-old star, which, on a cosmic scale, hasn't even opened its eyes yet. Surrounding it is a dust disk, and within that disk, two growing planets: PDS-70b, with a mass 5 times that of Jupiter, and PDS-70c, with a mass ranging from a few to 10 times that of Jupiter. But what they saw was even stranger. These planets had their own small disks around them. This meant they were actively feeding on the main disk and growing. For the first time, astronomers were able to directly observe what is known as a circumplanetary disk. In 2025, another system named HOPS 315 was analyzed. Here, something even more interesting was spotted: the very first stages of solid particle formation. What does solid particle formation mean? Imagine that in the colder regions of the disk, billions of tiny dust particles are orbiting the star. These particles are smaller than a micron, meaning 100 times smaller than a strand of hair. In HOPS 315, scientists saw these tiny particles sticking together. Materials like silicates and iron, the stuff that later becomes rock and metal, were condensing into solids and turning into larger particles. This is a gradual chemical-physical process where materials turn from vapor to solid. This was the initial step of planet birth, from dust to pebbles. But what comes next? When these pebbles reach a size of a few centimeters, a fascinating phenomenon called pebble accretion begins. Larger pebbles start to attract smaller ones, like a snowball rolling down a hill. The bigger it gets, the faster it grows. Within a few 100,000 years, which is incredibly fast on a cosmic scale, these pebbles turn into masses the size of mountains, then cities, then continents. At this stage, growth enters a dominant gravitational regime. Their gravity becomes so strong that they can pull in material from far away, slowly turning into bodies the size of the Moon or Mars. They can attract matter from a distance or shatter apart in violent collisions. If they can survive this stage, they get big enough to clear their surroundings and build a planetary core. Finally, if the core mass reaches about 10 times that of Earth, it can start sucking up gas from the disk and transform into a gas giant. But this path is neither linear nor guaranteed. At every stage, many factors can cause failure. Now that we know how planets form, let's go back to what scientists saw in PDS-70 and other disks. Scientists went into the data with a specific expectation. Old models had a clear prediction. Giant planets like Jupiter should form far away from the star, out where it's cold and ice exists. Why? Because to build a gas giant, you first need a massive solid core, and then you attract gas. But when they analyzed the ALMA data, they saw something weird. The location of planet formation turned out to be wrong. In a system called HL Tauri, rings of material were seen just 10 astronomical units from the star, the same distance where Saturn orbits in our solar system. These rings aren't necessarily the planets themselves, but signs of planets forming. This appeared far closer to the star than classical models predicted for giant planet formation. So, either planets can form in warm environments too, or they migrate inward very fast after forming. Neither of these was predicted in the previous models. This means the process of planet birth is much more complex than we thought. But a big problem remains. Do these clumps actually turn into planets? Because many of them are unstable. Inside the disk, the star's gravity, gas pressure, and friction with other particles are all working on the clump. Sometimes, instead of getting bigger, the clump breaks apart. Sometimes it falls into the star and burns up. Based on computer simulations and statistical matching with observations of hundreds of planet-forming disks, current models suggest that perhaps only a small fraction, around 10%, of these initial clumps survive to become full planets. Where does this number come from? First, from simulations showing that most clumps are destroyed due to orbital instability. Second, from observing disks that had all the right conditions but produced no planets. Third, from the high rate of collision and destruction in young disks. This means planet formation is a very inefficient process. For every Earth or Jupiter we see, dozens of other planets were never born. Now that we can see how planets form, we can figure out which systems have a chance. If a system doesn't have a rogue gas giant from the start, small planets get a chance to breathe. If the distances are right, liquid water can exist on the surface. If the orbits are stable, life has time to evolve. Of course, a rocky planet with liquid water is just a prerequisite for life, not a guarantee. Our own solar system was born from this exact same process. 4.6 billion years ago, there was a dust disk around the Sun, and within that disk, Earth was forming. But something strange happened. Jupiter moved. The grand tack shows that Jupiter was originally much closer to the Sun, perhaps just 1.5 astronomical units away, meaning slightly further than Mars is now. Why did Jupiter move inward? Because when a giant planet sits inside a disk, it interacts with the surrounding gas and dust, and this interaction causes its orbit to shift. Jupiter started drifting toward the Sun and was destroying everything in its path. But one thing saved it: Saturn. When Saturn formed, its gravity created a resonance, a gravitational harmony, with Jupiter, and the two pulled each other back outward. This migration allowed Earth to form. If Jupiter hadn't changed its position, Earth likely wouldn't exist, because Jupiter would have either eaten the material needed to build Earth or kicked Earth out of orbit. Now, the interesting question is, why did Earth become rocky, but Jupiter became gaseous? The answer lies in time and location. Earth formed in the warm region of the disk, where only metals and rocks could remain solid. That's why Earth could only build a small, rocky core, and the gas around it was very sparse. But Jupiter formed in the cold region, beyond the ice line, where water and methane are frozen. This area had much more material, so Jupiter could build a massive core and then start sucking in gas. That is why Jupiter has 318 times the mass of Earth, but is mostly hydrogen and helium. JWST has only just begun. Right now, we are seeing giant gas planets forming, but the next goal is even more exciting, seeing the birth of rocky planets like Earth. The problem is that rocky planets are much smaller and harder to see. But in the coming decade, with newer telescopes, like the Extremely Large Telescope, currently under construction, we will be able to see this too. Imagine one day being able to see signs of water forming on a rocky planet, or the moment an atmosphere forms around it. That isn't just planet birth anymore. That is witnessing the conditions where life can begin. When you look up at the night sky, visualize this in your mind. Millions of dust disks, at this very moment, are spinning around young stars. Inside each one, billions of particles are sticking together. Some will succeed and become planets. Some will break apart and be destroyed. Our own solar system was born from a disk just like that, 4.6 billion years ago. Maybe Earth isn't special. Maybe it's just one of the few planets that managed to survive all that chaos. Managed to capture water, managed to come alive. If you enjoyed this video, join the Astreon channel and hit the bell so you won't miss any of our upcoming videos.